Welcome to the presentation of my master's thesis on the determination of the magnetic octopole moment of 173 ytterbium and a design towards laser double resonance methods in a multi-reflection time-of-flight device. My thesis was a combination of two subjects relating to laser spectroscopy techniques. Here I will only cover the ytterbium study done in the University of Jyväskylä and must leave out the second part done in collaboration with CERN. Our understanding of the atomic nucleus is incomplete, as we presently don't have an effective theory for how protons and neutrons interact within the nucleus. Thus, further experimental data on fundamental nuclear properties is crucial for the development of advanced nuclear models. The interaction between the underlying electromagnetic moments of an atomic nucleus and its surrounding electron cloud provides a way to gain model-independent nuclear information. Over the past years, magnetic dipole and electric quadrupole moments have been measured in various nuclei from the atomic hyperfine structure, which consists of tiny splittings and changes in the atomic energy levels. However, higher-order terms such as the nuclear magnetic octopole moment are known for only few nuclei, as the measurements require very high precision and sensitivity. My thesis contributed to the octopole moment research by measuring it for atomic ytterbium with a sensitive laser spectroscopy technique. A surprisingly large octopole splitting in atomic 173 ytterbium was reported in 2013. This value, determined through measurements of the hyperfine intervals in the metastable 3p02 state, appears to be impossible to reconcile with any nuclear model presently on the market. Such a remarkable result thus called for an independent confirmation, which I did in my thesis using collinear laser spectroscopy at Iron Gate Isotope Separator Online IGISOL facility. In collinear laser spectroscopy, a fast atom beam is overlapped with a laser beam to achieve a sufficiently high resolution. By scanning the laser frequency in the rest frame of the atoms, it can be tuned in the resonance frequency of the electronic transition in the atomic shell. When the laser frequency corresponds to the energy difference between the hyperfine levels, the atoms will be excited. After being excited by the laser, the atoms decay back to the corresponding ground state, emitting fluorescence photons which can be detected by a photomultiplier tube, PMT. By measuring the fluorescence counts as a function of the frequency, the hyperfine splitting can be extracted. In my work, the ytterbium ions were produced with the offline ion source at the IGISOL facility. Isotope selected, cooled and then extracted as a continuous beam and guided into the collinear laser line, where they were neutralized using a charge exchange cell so that some of the atoms exit the cell in the metastable 3p02 state. Next, the atom beam was overlapped with a counter-propagating laser beam. The spectroscopy itself was performed using 3 optical transitions from the metastable 3p02 state. Hyperfine constants could then be extracted from the hyperfine spectra as detailed in my thesis. The results from the data analysis yielded consistent values for the nuclear electromagnetic moments, strengthening the confidence in the final values. The impact of the second-order hyperfine shifts was considered after my thesis in my co-authored article, and they were found to be smaller than our experimental uncertainties. Good agreement with literature is obtained for the hyperfine dipole constant A, but the values for quadrupole constant B and octopole constant C deviate. The final octopole constant value is 0.03 MHz at the 68% confidence level, which greatly differs from the literature value of 0.54 MHz. The origins of the deviation between these values are unclear. However, the literature value was extracted from a different transition at 770 nanometers. Further investigation using the same transition in the future might help to resolve this puzzle. To extract a value of octopole moment from the octopole hyperfine constant, nuclear structure calculations are needed. The new value is 0 within the uncertainties, but brings the nuclear theory and experiment into consensus. Based on our results, future measurements will require at least an order of magnitude improvement in precision to extract a non-zero magnetic octopole moment. In my article, we also reported on a set of atomic structural calculations of the second-order hyperfine shifts and the ratio of the octopole constant and moment which will be required to interpret such future high-precision measurements. Thank you for watching and thanks for the Finnish Physical Society for this opportunity to present my thesis.